So welcome to this next video in the playlist on Galois theory. In this video we're going to talk about solvability by radicals. So I'm going to start by making a definition which is, what does it mean for a polynomial to be solvable by radicals over a field? And this definition again relates to any field, so not just characteristic zero fields, although later in the video we will limit our attention to just characteristic zero fields, and we'll get to Galois' great characterization of when a polynomial is solvable by radicals over a characteristic zero field. So, oh no, not this. This should be little f, so I'm going to make it a little f. So let little f of x be some polynomial in the ring of polynomials over the field f, where f is denoting our field of arbitrary characteristic at this stage. What does it mean then for this polynomial? So question mark, what does it mean to say that this polynomial is solvable by radicals over f? So the definition I'm going to give you of this is that it means that if you look at the splitting field of the polynomial, so which I'll denote like this, split over the field f of the polynomial f of x, so that is the smallest extension field of capital F that contains all the roots of the polynomial little f. So if you look at the splitting field, this needs to be contained inside some radical extension of f. So we'll call that R. So this is actually the if and only if, definitional if and only if, for what it means for the polynomial f to be solvable by radicals over big F. It means that the splitting field of little f over big F is contained inside some radical extension of f. So R is some extension of f that is radical. And what that's going to mean then is that all of the roots of the polynomial f, little f, are going to be expressible by radicals of f. So that's actually another term we might sometimes use, and this is what I mean by it. So if I say that all the roots of the polynomial are expressible by radicals over f, what that means is exactly this. It means that all of the roots are contained inside some radical extension of f. And this, by the way, this is just the field adjoin all the roots of the polynomial. So if the polynomial has, let's say, n distinct roots, alpha 1 to alpha n, and it might not necessarily be the case that this polynomial is separable, so it might not have its degree number of distinct roots, but that doesn't matter for this definition. So, or indeed, the concept of what a splitting field is. The splitting field, the smallest field that contains all the roots of the polynomial is this field, f adjoin alpha 1, alpha 2, all the way up to alpha n, and that is the splitting field. The splitting field's definition is the smallest extension of f which contains, in which the polynomial splits, and therefore it's the smallest extension of f which contains all the roots of the polynomial f. So, yep. If the roots of a polynomial are expressible by radicals over f, all it means is that all the roots are contained inside some radical extension, which is to say that the splitting field of the polynomial over the field f is contained inside some radical extension of f. So that's what it means for a polynomial to be solvable by radicals over f. We will relate this in the next video to the existence of formulas. Here we're just going to take this concept a little bit further. So we're now going to assume that the characteristic of the field f is 0, and we're going to make this better. So for characteristic zero fields, there is a theorem that is going to take a considerable amount of proving, but which we will prove, which is that any radical extension of a characteristic zero field is contained inside some solvable extension, some finite solvable extension, and I'll define that in just a moment, and vice versa. So if you have any finite solvable extension of f, it's contained inside some radical extension of f. So I need to define what I mean by a solvable extension. So a solvable extension, and also what a finite solvable extension is. That's more obvious. A finite solvable extension is just a solvable extension that is also a finite extension. But what is a solvable extension? A solvable extension is firstly a Galois extension. So that means it's normal and separable. Not necessarily a finite Galois extension. This definition applies to infinite Galois extensions also. But of course, we're doing basic Galois theory here, so we're only going to be dealing with finite Galois extensions and finite solvable extensions. So thankfully we don't need infinite Galois theory here, but these definitions do go over into infinite Galois theory. So a solvable extension is a Galois extension in which the Galois group, so gal of S over F, so S is our solvable extension of F, so we can use this picture here for this, needs to be a solvable group. That's the definition of a solvable extension, a Galois extension in which the Galois group is a solvable group. So I'll just remind you what a solvable group is. So it doesn't necessarily need to be a finite group to be solvable. Again, we'll only be dealing with finite groups here, but the definition does go across into infinite group theory and infinite Galois theory. But the definition of a solvable group is that your group should have a chain of subgroups inside it, going down to the trivial one, which I'll denote by this fancy 1 here, so that just means the trivial subgroup. And then you should have a chain of normal subgroups, so H1, H2, H3, etc., all the way up to, let's say, some Hn. And we might just call Hn G. So Hn is the entire thing, but then there's some Hn minus 1, which is not the entire group G. And we could let 1, the trivial one, be H0 then to make our notation nice. So you need to have a chain or an ascending sequence, finite sequence, which we often call a chain, this ascending chain of subgroups that are all normal in the one above them. So if we draw a little picture of this, so you've got like the whole group here, you've got the trivial subgroup just containing the identity there, and then you've got this sort of chain of ascending, so that's 1, then this next one is H1, then the next one outside that is H2, and then you ascend up gradually until you get to the whole of G, and each one, so if you take this one here, let's say, which is H3, and then it's contained inside H4 here, it has to be a normal subgroup of the one above it. So there has to be this ascending chain of normal subgroups inside G. And there's an additional requirement such that if you quotient HI out by the one below it, which is normal inside it, that this quotient group that you get needs to be abelian, and that needs to apply for each relevant one. So Hn over Hn minus 1 needs to be abelian, all the way down to H1 over H0 needs to be abelian. So it's for all I from 1 to n here. So that's the meaning of the group being solvable, that there needs to exist a ascending chain. It doesn't say anything about how many of them it is. It doesn't say that all ascending chains of subgroups have to obey this, not at all. It just means that there has to be one. You have to be able to find some ascending chain of normal subgroups like this inside your group where all of the quotients are abelian. If such a chain exists, then the group is called a solvable group. And if you have a Galois extension where the Galois group is a solvable group, does have such a chain, then we call that extension a solvable extension. And if the extension is a finite extension, then we would call that a finite solvable extension. So, as I was saying then, in characteristic zero fields, it is the case that any radical extension is always contained inside a finite solvable extension, and indeed also any finite solvable extension of a characteristic zero field will always be contained inside a radical extension. Now this is going to take some proving, and I'm not going to prove it in this video. We're going to come to it later. We're going to need a very, very good understanding of Kummer extensions and cyclotomic extensions to be able to argue this. But if we believe it for for now, if you take it on faith from me that this is true, we can now do a lot with this. It's actually quite easy now to prove the non-existence of the quintic formula for characteristic zero fields. If you believe this is where all the effort is. This is the huge thing that needs proving. But we're going to omit the proof of that for now and just carry on with the argument. Because this is the fun bit, proving that those two lemmas, if you like, the two containments, is hard work and not particularly fun. The bit that comes after it is actually very fun. So we're going to go with the bit that comes after it. So now, if we think we're going to take further, we're going to update our condition for a polynomial being solvable by radicals over some field for the case that the field is characteristic zero with what I've just told you. So we've already said then that a polynomial little f is solvable. Sorry about that, just having some technical issues here. It's been a long time since I've used this thing, and I'm managing to click a whole bunch of buttons and do a whole bunch of things, ending up pausing the recording without realizing that I am. So apologies for that. So we've already said that a polynomial little f is solvable by radicals over big F if and only if the splitting field is contained inside some radical extension of F. But now we know that a radical extension is going to be contained inside a solvable extension, and also that a solvable extension is always going to be contained inside a radical extension. So actually we can update our condition to, in the case of characteristic zero fields, it's going to be solvable by radicals over F if and only if it's contained inside a finite solvable extension of F. And I apologize if I missed the word finite in what I was saying just a moment ago. So I'm updating our condition now for the polynomial little f being solvable by radicals over big F to it's solvable by radicals over big F if and only if the splitting field is contained inside a solvable extension, a finite solvable extension. Sorry, I missed the word finite again. Contained inside a finite solvable extension of F. And the reasoning for that, just to go over it one last time, is that we know it's solvable by radicals over big F if and only if it's contained inside a radical extension, and we know that that implies that it's contained inside a solvable extension, so that proves one direction. The other direction is then, if it's contained inside a finite solvable extension, then we know that that finite solvable extension will be contained inside a radical extension, and therefore that implies that the polynomial will be solvable by radicals over F. In fact, I might just write this out to be absolutely clear. So let's abbreviate. So solvable by radicals over F, that's what that means. So we know this is if and only if the splitting field, which I'll denote SP, is contained inside a radical extension. And then this forward direction is easy. Well, it's not easy, but from what I've told you, we're assuming the field has characteristic zero now. We now know that it being contained inside a radical extension implies that it's contained inside a finite solvable extension, which we're denoting S. So that is that direction. Now, how do you argue the opposite direction? Well, if it's contained inside a finite solvable extension, then I've also said that that implies that it will be contained inside a radical extension, which proves this thing, and then that proves this because that's the definition that we've made. This is a definitional if and only if, and this if and only if follows from the two unproven lemmas that I have stated for characteristic zero fields. So now I can just, say that this if and only if this now. So a polynomial little f is solvable by radicals over big F if and only if it's contained inside if and only if the splitting field is contained inside a finite solvable extension of F. Now let's do some Galois theory. Sorry, I keep wanting to move the page up, but I mustn't because then I move my hand too much onto the iPad here and then I end up clicking things that I don't want to, so I need to keep it like this. So we've got our field F here, we've got our splitting field here, and we now know that this being solvable by radicals is if and only if it's contained inside a finite solvable extension S of F. So this extension is a finite solvable extension, meaning it's a finite Galois extension and the Galois group is solvable. Now comes the bit of Galois theory. So the splitting field of any polynomial over a characteristic zero field is always a finite Galois extension. So this extension here is finite Galois. And you might worry, you might say, oh, is that always the case that splitting fields are always finite Galois extensions? Yes, in characteristic zero it is. And you might say, well, what I learnt that a finite Galois extension is a splitting field of a separable polynomial. What if this polynomial isn't separable? Well, this is the beauty of characteristic zero. So characteristic zero tells us that all irreducible polynomials are separable. That you cannot have irreducible, inseparable polynomials in characteristic zero fields. It's a horrible complication that happens in characteristic P, that some irreducible polynomials end up being inseparable. In characteristic zero, though, it's gone. It's not there. It's not a problem at all. So I can split the polynomial f into its irreducible components over big F. So let's write these out. So let's say it's f1, f2, all the way up to fk. So each of these individual polynomials is now irreducible. So this is the polynomial f split into its irreducible components, and each one of these will be separable. It will have its degree number of distinct roots. Now, some of them might occur with multiplicities, so it might be the case that f2 is the same as f1. So I might be able to split this into, in fact, let's say f1 up to fk are all distinct irreducible polynomials, and then we have some exponents here. Two different irreducible polynomials do not have roots in common. That's a basic fact from field theory. You don't need the field to be characteristic zero. That, thank goodness, holds even over characteristic P. So these two different irreducible polynomials, f1 and f2, will not have common roots. All their roots will be disjoint from one another. If you have the set of roots of f1 and the set of roots of f2, they do not overlap. And that's because, the irreducible polynomial will be the monic version of that will be this minimal polynomial of the element. So you can't have, if these two polynomials, f1 and f2, had a common root, then that element that is the common root, what on earth is its minimal polynomial going to be? It can't be f1 and f2, or the monic versions of f1 and f2, because they're distinct. I'm assuming, by the way, that f1 and f2 are not related by some constant factor. That's something I should have actually said. So I should put out here a constant factor. So let's assume f1, f2 all the way up to, and I've now double used k. Oh, how annoying. So let's call that k0. So I'm assuming f1, f2, fk are all monic polynomials, irreducible, and therefore they are not equivalent in any way. So I've pulled out this constant factor k0 here. So that's the constant factor that was potentially in f out the front of f. If you pull that out, f becomes monic, and then these are its monic irreducible factors. So f1, f2, f3, f4, all the way up to fk, they do not have common roots with one another. So then, basically, this splitting field will be the same as if I got rid of the k0, got rid of the multiplicities, and just had f1, f2, all the way up to fk. And this polynomial would now be separable. So this splitting field of my original f, if f was an inseparable polynomial, it had multiplicities in its roots because not all of e1, e2, all the way up to ek were 1, it doesn't matter because its splitting field will still be the same as this polynomial. Taking out those multiplicities does not change what roots you need to join on. And this polynomial, this is now a separable polynomial, therefore this is the splitting field of a separable polynomial, ergo it is a finite Galois extension. Ergo the splitting field of the original polynomial, which granted wasn't separable, is still going to be a finite Galois extension because it's the same extension. The problem in characteristic P that occurs is that you have irreducible polynomials that are inseparable. In characteristic 0, we don't have such things, and therefore even if you have inseparable polynomials, it occurs in this trivial way, basically. This is the crux. The only way that you can get inseparable polynomials in characteristic 0 is this trivial way, by having the factors, the irreducible factors, to higher multiplicities than 1. In characteristic P, it's far uglier. You can end up with inseparable polynomials not because of this happening, but because the actual irreducible factors are inseparable. Anyway, so all of that was to basically justify why the splitting field of the polynomial little f over the capital F is going to be a finite Galois extension. And now we use Galois theory. So this is a finite Galois extension, which I'll abbreviate as FG. This is also a finite Galois extension here. So this means that this is a Galois subextension of S. So we know what that means. There's a Galois correspondence tells us stuff here. It tells us what the Galois group of the splitting field of little f over big F over F is going to be. So the Galois group of splitting field of little f over big F over F. So the Galois group of this extension here, and I apologize, I would like to use the pointer rather than having to continually draw things, but I don't trust myself. I end up pressing stuff that then ruins the recording, so that's why I'm instead just making a mess. So the Galois group then of this extension, the Galois correspondence tells us if it is the case that you've got a sub-extension of a finite Galois extension, you can work out what its Galois group is going to be by looking at the Galois group of this extension and looking at the Galois group of this extension. So it's going to, hopefully you recall this from basic Galois theory or Galois correspondence. This is going to be the Galois group of S over F, so the Galois group of this extension here, quotiented out by the Galois group of S over the splitting field. Whoops, run out of space, so let's just go a bit. So the Galois group of the splitting field of little f over big F. So it's in the case that you have a normal subextension, which is a Galois subextension. So this Galois correspondence tells us that if you have a Galois subextension like this in another Galois extension, then you can get the Galois group of this one by quotienting out the Galois group of this by the Galois group of this. And that's what we're doing here. So the Galois group then of the splitting field of little f over big F over F is isomorphic to the Galois group of S over F, quotiented out by the Galois group of S over the splitting field of little f over F. Now, because S is a finite solvable extension, we know that this is a solvable group. It is a fact from group theory, which I'm currently debating whether to bother proving, that if you quotient out a solvable group by any subgroup, whatever subgroup you like, well obviously it needs to be a normal subgroup, but if you quotient it out by any normal subgroup, then the quotient you get will always be solvable. So this is going to be a solvable group, is the point. So that then forces this to be solvable. So what I've just proven is, if we go back up to our string of if and only ifs, so I've just proven that if the splitting field is contained inside the finite solvable extension, that this then implies that the splitting field is itself solvable. So it's a solvable extension. So we already knew it was a Galois extension. I argued that here, where I argued why the splitting field of any polynomial in characteristic 0 is always a finite Galois extension. And we've just proven that its Galois group is solvable, ergo it's a solvable extension. It's a finite solvable extension. I could actually add that in, finite solvable. And then the backwards direction is trivial, you know. If the splitting field is a finite solvable extension, then clearly the splitting field is contained inside a finite solvable extension because it's contained inside itself. So you can use S as the splitting field there. So basically what I've done is produced another if and only if statement here. So I can now update the condition of being solvable by radicals over F to it's if and only if the splitting field of the polynomial is a finite solvable extension. So I suppose I should give you at least some of the arguments as to why the quotient of a solvable group is always another solvable group. So this isn't difficult. You basically just follow your nose. This is a question that if it came up on an exam and you had never seen it before, you might get a little bit worried that, oh, this looks like a quite textbook proof, maybe I should know the argument as to how you do this. But actually, if you just thought about it enough, you would probably be able to come up with this. So you just have to write down the definitions and hope that what you need to do pops out. So I don't want to have to redraw the. Here we go. This, remember, is the definition of a solvable group, that there exists this ascending chain of normal subgroups in which the quotient of 1 by the under 1 is always abelian. So now, if I take some subgroup, what should I call my subgroup? N, let's say, a normal subgroup, so we'll call it N. So let me just bring this up because I don't want to press buttons. So if N is a normal subgroup of G, I want to argue why G quotiented out by N is also a solvable group. So how are we going to do this? So I probably am not going to go through this full argument, but I'll give you at least the pointer. So, you have this canonical group homomorphism from G into G quotiented out by N, and I should really use pi instead of phi because pi is more typical to use because it's often referred to as the canonical projection of G onto the quotient group, and therefore you use pi because pi is the Greek letter equivalent to P, and P for projection. So this just maps any element A onto its coset in the quotient group, so I'll call that a bar. So what you can then do is take the image of all of these subgroups. So you have your ascending chain of normal subgroups. So now just look at the image of this. So it would be nice to draw this out below it. So you'd have pi of 1 here, which will just be the identity in G quotiented out by N. Then you'll have pi of H1, pi of H2, etc., all the way up to pi of Hn, which is, as Hn is G, that will equal G quotiented out by N. So you basically get an ascending chain of subgroups inside the quotient group by doing this, because the image of any subgroup under a group homomorphism is always going to be another subgroup. So all of these images here, pi of H1, pi of H2, they're all subgroups. So we've certainly got a ascending chain of subgroups here. And I apologize, I'm kind of doing this over the top of another picture. I'm just too lazy to redraw it all out. What you then need to do is argue why all of these subgroups are still going to be normal in one another. So you'd have to think through why they're all still going to be normal. And then you'd also have to think through then when you quotient one out by the other. So if you take pi of hi quotiented out by pi of h minus 1, why is this going to be abelian? Because this is how you're going to construct this exact chain that I've produced here. This is going to be the ascending chain of normal subgroups where the quotients are abelian to prove that G quotiented out by N is a solvable group. So you'd have to also argue why these are all going to be abelian. So certainly proving that they're all still normal inside one another is not difficult. I might, in fact, shall I just complete this proof? It's annoying if I set it as an exercise to the viewer. So fine, let's do this. So why is it the case then that pi hi minus 1 is even normal inside pi hi? So let's take any element A inside pi hi minus 1. Let's take any element B inside the larger subgroup pi hi, and then let's do B inverse, and we want to argue why is this in pi hi minus 1. So we want to see why does conjugating by any element of the larger subgroup land you back inside your smaller subgroup. So basically we just have to say, well, A is going to be, it's going to have some element in G that's mapped onto it, So we'll call that, I might in fact call these elements the bars, so that it would just make the notation better. So a bar is some element inside pi hi, and it has some a inside g that is mapped onto it. Similarly, b bar has some b inside g, which is mapped onto it. So then we can view this as pi of b, pi of a, times pi of b inverse, but pi of b inverse is the same as pi of the inverse of b. So I'm saying here that pi of b, which is what I'm replacing b bar with, its inverse is the same as pi of b inverse. So hopefully that's a basic fact about group homomorphisms that you're aware of. So this element then becomes this, and then just join them all together by the laws of group homomorphism. So it's pi of BA B inverse. BA B inverse. Oh, now we need to make a little argument. Okay, fine. We need to say, that A, if A bar is in pi of hi minus 1, then A is going to be in hi minus 1. So A is an element of hi minus 1. Similarly, B, because B bar is an element of the image of hi under pi, that will imply that B is an element of hi. So then what we've got here is we're conjugating some element of hi minus 1 by some element of the larger hi, and therefore, because hi minus 1 is normal in hi, this is going to be an element of hi minus 1. So therefore, pi of BA B inverse is therefore going to be inside pi of hi minus 1, which if you look up here is exactly what we wanted to show. So that's how you show that each of these subgroups here is normal inside the next one. So then the more difficult thing, which I might just sort of wave my hands at a bit, is why quotienting out. Why, when you quotient them, do you still get something that's abelian? It's because it's going to be a subgroup of the quotient group of the original thing. So, pi of hi quotiented out by pi of hi minus 1, it's going to be not some normal subgroup necessarily, but some subgroup, which I'll denote like this, not necessarily a proper subgroup. It'll be a subgroup of hi quotiented out by hi minus 1. And this is abelian because the original group was normal, and that's then all we need. So why I should give you some sort of argument as to why this is going to be true. It's because if we have hi here, let's say this is hi, and then we're quotienting out by hi minus 1 here. So this is us splitting hi into the cosets of hi minus 1, like so. Then what we're doing, how do you do this? When you map them under pi, your things that are in the same coset here are going to be mapped to the same, I might need to pause just to think for a moment, and then I'll come back, I'll explain this. So it's a good job that I did stop to think, because I tried to think a lot, and I tried to think of a proof that this is true, but I haven't actually been able to think of a proof that this is true. So I'm not actually even sure whether this is true. So I'm going to cross this out because I don't know whether that actually is true. If it is, it might still be true, but I can't prove that it's true, or I haven't been able to, in the last 20 minutes of thinking, been able to prove that it's true. So instead I've come up with a different way that we can prove that pi hi quotiented out by pi hi minus 1 is abelian. And unfortunately, the argument that I was going to try and give you, which I'm not sure actually works, used simpler group theory. It was just going to either use the second or third isomorphism theorems, whereas now I'm going to use the argument of commutators. So I'm sorry if you're not well up on this sort of group theory, but hopefully you are. So this will be abelian if the commutator subgroup of pi hi, which we'll call pi hi prime, so the derived subgroup or the commutator subgroup, if this is contained inside pi hi minus 1, then this quotient will be abelian. So what we know, of course, is that because hi quotiented out by hi minus 1 is abelian, we know that hi prime is contained inside hi minus 1, and this is then going to allow us to prove this. So we need to show that the commutator subgroup is of pi hi is contained inside pi hi minus 1. So let's just take an arbitrary commutator of elements inside pi of hi and show that it's inside pi hi minus 1, and that will prove that the commutator subgroup is inside it. So let's let a bar and b bar be elements of pi hi, and let's take the commutator of a bar with b bar, which by definition is a bar inverse b bar inverse a bar b bar, and we want to argue why is this going to be contained inside pi hi minus 1. So that's what we want to prove. I'll put want to prove here. So of course now we just say, well, a bar is going to be pi of a for some a inside hi, and a bar inverse is then going to be pi of a inverse. Then we've got pi of b inverse for some b inside hi, so a and b are both elements inside hi. And a bar is pi of a, and b bar is pi of b. So we've just basically gone to their pre-images, or one of their pre-images, under pi, and then we just combine this obviously all together to say that this is pi of a inverse b inverse a b, which is pi of the commutator of a and b. And then because the commutator of hi was contained inside hi minus 1 because the quotient was abelian, that's how we know that, then we can conclude that the commutator of a and b is an element of hi minus 1, and therefore pi of the commutator of ab is an element of pi of hi minus 1, and therefore follow this back, so we therefore have exactly what we wanted to show here. So that's an argument, therefore, as to why these quotients are abelian, because I can prove that the commutator of this thing is contained inside this subgroup here, from the fact that the commutator of hi was contained inside hi minus 1 because the quotient was abelian. So hopefully you're aware of the brilliance of the theory of commutator subgroups and how a quotient is going to be abelian if and only if the normal subgroup contains the commutator subgroup of the larger group that you're quotienting out. Okay, so where were we? So I've just given you the argument then as to why, if you have a solvable group, why, if you quotient that out by any normal subgroup, the thing that you end up with is still a solvable group. And we've used that to conclude then that in characteristic 0, a polynomial f is solvable by radicals over big F if and only if, and we've got it all the way over here, if and only if the splitting field of that polynomial over the field F is finite solvable. And this, by the way, this is Galois's great achievement. This is the Galois characterization of when a polynomial is solvable by radicals over a characteristic 0 field. So I'll state it one last time, or well, not for the last time, we're going to use this a lot going forwards. But a polynomial is solvable by radicals over a characteristic 0 field if and only if the splitting field of that polynomial over that characteristic 0 field is a finite solvable extension. I think we will leave it there. So in the next video, we're going to take this and use this to prove that in characteristic 0 fields, there will never be a quintic formula, and there will never be a formula for any higher degree polynomials than 5. And then after we've done that, we will come back to proving this, which is the lemma, or the lemmas, the two sides of this lemma that we didn't bother proving, which is that for characteristic zero fields, radical extensions are always contained inside finite solvable extensions, and finite solvable extensions are always contained inside radical extensions. That takes some work, and that's really what is actually difficult about this proof. It's all in there, and we skipped that for now. We said if you believe that, then this follows. So I'll see you in the next video.